Hi everyone, welcome to my video. In this video, I'm going to show how do we investigate on the stability of a closed-loop system. So let's consider a typical third-order systems with known zero, with a variable gain k and unity negative feedback. So I'm going to use Routh Hurwitz criterion to find out the stability of the system of the range of the gain k that will cause the system to change its nature in terms of the stability. First, we will need to find out what will be the characteristic equation, and to get the characteristic equation, we need to find out what will be our TS. So in this case here, our TS will be equals to K multiply GS divided by 1 plus K multiply GS. And if we set the denominator of the closed loop transfer function equals to 0, and we will get this characteristic equation. From the characteristic equation, we can build the Routh table, and we basically, for the first two rows of the Routh table, we are actually substituting the coefficients of the polynomial as such. The remaining two more rows here, we are going to use the product of the diagonal elements to calculate out what will be the remaining terms. To get the first term over here, we will need to cross multiply 26 and 125. This is plus, and the product of it, we will have to minus the diagonal product of 1 and 100 plus k, and in the end, we are going to divide back by 26. It will be 26 multiply 125 minus 100 plus k and divided by 26. Final product will be 3150 minus k divided by 26. And because we have an empty column over here, which have nothing, and hence we can say this term will be always 0. And next, we need to calculate what is this term over here. And using the similar manner, we need to cross multiply the terms two rows above, which is this plus, and then minus the diagonal product of 26 and 0, and finally divide back by this term. In the end, it will be 100 plus k. And to evaluate the stability of the system using Routh table, we will have to observe the first column here. And in this case here, we will be only interested to find out what will be the marginal stability. Because if we can find out the marginal stability, we will be able to evaluate the stability of the system. In this case here, we'll be interested in the elements in the first column that is potentially goes to 0. In this case here, the only possibility for the first column to have at least one 0 will be this term. And to make this term goes to 0, this will imply that my k will be 3150. And this will be my critical gain. At this critical gain, we are going to expect the system to exhibit undamped response. That means a sustained oscillation. But we also need to know whether the stability range will be higher than 3150 or lower than 3150. From the first column, we can see that if k is larger than 3150, this term will become negative, and negative will cause a sign change in the first column, and hence the system will be unstable. On the other hand, if k is less than 3150, then we can observe all terms in the first column of this Routh table are positive, and hence no sign change, and therefore the system will be stable. To summarize, if k is less than 3150, the system will be stable. And when k is equals to 3150, then the system will be marginal stable. And when k is larger than 3150, the system will be unstable. So with these simple tools, we are able to determine the stability of the system. Let's proceed to use MATLAB to verify our solution. Using the seesaw tool available in MATLAB, we are going to investigate whether stability criteria is valid. From our answers earlier, we say that any gain value lower than 3150, the system will be still stable. We can see that in the top left corner, we can adjust the gain of the compensator, which means in this case here our k value. And when k is equals to 1 by its default value, we have all the roots at the left hand side of the S-plane and giving us a stable system. If we adjust the gain of the k to any value, as long as below 3150, as you can observe here, so we can try with 1009, we can try with something lower, 900 plus, or we can actually shoot up to 2158, the system will be still stable. But if we set the gain to be exactly 3150, you can see that roots are now located exactly on the imaginary axis and giving us a sustained oscillations, which means the system it is now in undamped response. And if we apply a slight gain above 3150, in this case here, we just put additional 0.05, the system will become unstable. And of course, as we can predict here, any value larger than 3150 will cause the system to be unstable, as you can see from here. So with this, our solution here is verified. That's all that I want to show in this video. Thank you very much for watching. Bye.